All right, let's get started. Let me show you the slide. So we have studied almost all the instruction, RB32I is providing. Look at this, right? Last time we went through this table, right? So the only remaining instruction we have to talk is what? Set less than instruction, the thing we skipped last time. So, before we jump to, so we almost finished the instruction discussion. So before we jump to new topic, which is CPU design, okay? CPU microarchitecture, internal structure design. Before we jump into new topic, let me finish the things we skipped last time. Set less than instructions and Endianness stuff, right? So first, set less than instruction. It is instruction itself is very simple. Set less than. This one, Minchang, can you please?
For instructions that help you set the conditions. SLT, SLTI for signed numbers, SLTU, SLTIU for unsigned numbers. Instruction format is as follows.
Okay, thanks. Set less than instruction, right? First, what is this instruction for? Look at this. So the function of each function of the set less than, very simple. If the first source operand RS1, take a look at this example. If S0 is less than S1, right? First source operand is less than S1, second source, then set T0 register to 1. Otherwise, T0 becomes 0, right? So instruction itself is very simple, right? So you basically you want to compare these two numbers, right? These two numbers, you consider these two as signed numbers in this case, set less than immediate. Okay, these two instructions you consider first and second source operand as a signed number. And in this case, you have a U suffix, set less than unsigned, right? So you consider these two numbers as unsigned numbers. That is only difference. Okay, and I. Okay, if you have I, that means what? Second source operand. You want to specify constant, immediate, right? Same thing goes to here, right? So SLT, SLTU are using R-type encoding, right? R-type encoding, and these two are using I-type encoding. So instruction itself is so simple. The question is then why? Where do you think you can use those instructions? There should be some purpose of creating that instruction, right? So I can think of two different usage cases. Okay, so in high level language example. So how about this? So sometimes you want to use Boolean data type like this. Boolean. Bool, is it correct? Okay, so Boolean data type and bool, right? Is it correct? Right? Is it correct? Bool. Okay, bool. I don't have a header file, so we have to use this underscore bool. Okay, and bool. Let's say test one. Okay, so Boolean data type. So test one can be either 0 or 1, right? Boolean, right? And you say integer A and B. So sometimes you want to write this kind of code. Test one, A. How about this? If, right? Integer. That means that is signed numbers, signed integers, right? So if A is less than B, how to interpret this statement? A is less than B, you know, test 1 is true. True means what? True is 1, right? Otherwise, false, right? False is what? Test 1 is 0. So if you compile this code, did I save it? Okay, test this code, compile it. Syntax problem. What is that? B redeclared. Okay, B. Okay, here argument, right? Argument and local variable. So redeclared, right? So I made mistake. So let's remove, right? Let's remove this. This one is okay. So we are taking B and C from argument, right? Compare just A and B. Okay, test 1 set but not used. And right here, test 1 is set here, but not used afterwards, the warning message. So why do you set this test 1, given that you don't use that test 1 afterwards, like warning, right? Doesn't matter, right? Okay, so check out this dump. So if you check out this dump, right? Take a look at this one. Set less than instruction, right? A4, A5, okay? Compare these two. A4 is less than A5. A4 is less than A5, then A5 becomes 1. Set less than. So the reason why compiler used SLT is because B and C, right? B and C are signed integers. Signed integers, right? So what if you then write this code, unsigned, right? I want to declare unsigned local variable called D and E. Okay, and I want to do this test 2. Okay, test 2. D about this. Okay, if D is less than E, then Boolean data type test 2, right? True. True means 1, right? So then compiler would use SLTU instruction for that, right? Okay, warning message you can ignore. Look at this. Compare this, right? Test 1 and test 2. Here, SLT, SLTU, right? So depending on data types you use, compiler select the right instruction for you, right? And one more example. What if you do this? Test 3. Here, let me, what if you do this? You want to compare D and 7. If D is less than 7, constant or immediate, right? And that is true. So if you compile this, test 3. By the way, if you have webcam, yeah, please turn on your video. Only Dongwoo turned on his video. Okay. Here, look at this. In this case, right? SL test 3, SLTIU, immediate and unsigned, right? You are comparing two unsigned number. So in this case, right, 7 unsigned number, right? So SLT, I, immediate and unsigned, right? 7, right here. Okay, that is first usage case, okay, of this instruction. You can use those instructions. And second usage case, I'm not talking about this in detail. Okay, one more thing. Okay, this one. This one, Juyong, can you please? Microphone turned off, Juyong.
I'm sorry. Immediate in SLTI and SLTIU are sign extended. Immediate in SLTI is treated as signed number. immediate in SLTI, U is treated as unsigned number.
Okay, thanks. As when you design, hardware, think about that. Okay, so we will talk hardware design from next week. But here, think about hardware structure to execute that SLT instruction. You have ALU, right? ALU will do some comparison, right? To execute SLTI instruction, right? T0, T1, and some constant like what? 4. So if T1 is less than 4, that will become 1. Otherwise, 0, right? So to execute, that means to compare, right? You have to compare these two, source operand. So what do you have to do? What do you think? What do you have to do in hardware? Compare, right? Comparison. So probably you have to ask ALU, right? This ALU to do subtraction, right? Subtraction first. Then check something. You don't know for sure what to check, but you are thinking about, okay, I have to ask ALU to do subtraction, right? Supplying 4, T0, T1, and 4. And ALU is able to do many different operations like addition, subtraction, AND operation, OR operation. So you have to ask, right? Specifically, okay, do subtraction, right? Some control signal. Then you can observe this output, okay, why? To figure out, which one is smaller, right? Okay, so that is data path, right? We are talking about 32-bit CPU, right? ALU is taking 32-bit input, 2 of them, then generate 32-bit output. So that slide is talking about the same issue we discussed a few weeks ago, right? Second source operand is provided as an immediate here, right? So I-type instruction, do you remember the encoding? I-type encoding, this one? Here, I-type encoding. So immediate is specified here, okay? First 12-bit. So from this 12-bit, somehow you have to create, so 12-bit immediate, right? From this instruction, you take out the first 12-bit immediate, and somehow you should create 32-bit number. So that box will be, some logic, sign extension logic. So based on that sign bit, okay, the last bit, so you create 32-bit, 20-bit, right? 20-bit, 12-bit, so 32-bit, right? So you duplicate, right? This sign bit 0, then or upper 20-bit will be 0, 1, or upper 20-bit will be 1s, right? Sign extension. So the important thing you have to remember is regardless of data type. So SLTI, okay? So that means what? That means you consider these two as signed numbers. So 4 is signed numbers, right? This one is a signed number. And if you use SLTIU, then SLTIU, T0, T1, and 4. So that in this case, you think of it as unsigned number, right? Unsigned. And RISC-V specification says, I don't care about signed and unsigned, right? These second operand of these instructions, second operand, right? Immediate, will be sign extended all the time. I don't care, okay? SLTI, I don't care about SLTU. It will be sign extended. You have to design this sign extension logic, okay? For both for both these instructions. Okay. It is very similar to what? Add instruction. Remember? So second source operand is sign extended. Add instruction is add I, right? Add I instruction, right? So that immediate is a sign extended. And in case of logical instruction, this one, that immediate, that is also sign extended, right? Immediate in AND I, OR I, XOR I, basically second source operand, that is sign extended. That sounds a little bit weird, right? Because in this case, AND operation, logical operation, right? So I'm explaining this again because it is a little bit confusing, right? T0, T1, some immediate, okay, like some sequence of ones and zeros, 12-bit immediate, some sequence of ones and zeros like 0, 7, F. One example, right? So RISC-V CPU take that instruction, okay, and extract this immediate here 0, 7, F. So in this case, MSB is 0. If you do sign extension, this 20-bit will be all zeros, right? So sign extension logic will do that operation. So that means, if you do sign extension, it sounds like you think of it as signed number, right? Signed number. But typically AND operation, right? You don't think this constant as signed number, right? You are thinking this constant as sequence of ones and zeros, right? AND operation, right? AND gate, right? AND gate. So you don't think of it as signed number, right? Nevertheless, RISC-V CPU will do sign extension. That is something weird, but there is no choice. We have to follow the specification. We don't have any choice, right? RISC-V architect specifically explicitly said, okay, second operand will be sign extended. Okay. So we don't have any choice. So implication of that statement is, let me show you some assembly code here. So we have 12-bit immediate, right? So can you set less than? Can you write this instruction? SLTI, okay, SLTI, T0, T1, 12-bit immediate, okay? So 7FF, how about that? Can you write this code? Yeah, no problem, I think, right? So 7FF, the compiler will take a look at, okay, 7FF. Can I create 7FF? So look at this, right? Here in this ALU, this CPU block diagram. So the issue is, can you create 7FF? Can you supply 7FF from instruction? From SLTI instruction? CPU, right? CPU patch it, read SLTIU instruction, and taking out, and we'll take out the first 12-bit, send it to sign extension logic, and that logic will do sign extension and supply it to ALU. So the issue is, can you create 7FF here based on that instruction? Yes, right? So you supply 7FF, right? You take out 7FF from instruction and sign extension logic, right? MSB is 0, right? 7 is what? 0, 1, 1, 1, 7. So MSB is 0. So if you do sign extension, you can create this number. So there should be no problem in compilation. Okay, so take a look at machine code, right? You have 7FF here. Okay, then one more example is, can you then create this number? Let me copy and can you create this? How about that? FFF. That means, you know, FFF or 12-bit or 12-bit FFF, right? So what is the intention of that instruction? So you want to do AND operation, right? T0, then 32-bit, right? 32-bit, 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 AND gate, right? 32 AND gate. So your intention is I want to do AND operation of these two, T0 and this number, this value. So then question is, do you think compiler can generate this code? So can you create? The issue is, can you create based on instruction, SLT, I instruction, can you create here, this point? Can you create this number? This number? CPU can create this number based on the instruction. CPU patch it? No, it cannot, right? So because FFF, right? So one, then CPU will do, hardware will do sign extension based on this MSB. So that means output will be all Fs, 8 Fs, 8 Fs, right? So CPU, this sign extension logic cannot cook up that specific constant, specific sequence of ones and zeros. So if you compile it, okay, compiler gave up, right? I cannot create that illegal operand. Okay, so then one more example. Can you then put this number 8 Fs? How about that? So the end goal is okay, CPU, okay, ALU. Can you supply that 8 Fs? Okay, 8 Fs to ALU after going through this process. CPU can create this number, this sequence of ones. Yes, because immediate is 3 Fs, then MSB is 1. So based on MSB, the 20-bit will be set, right? Then the output of sign extension will be this sequence. So if you compile this code, there should be no problem, right? No problem. It sounds very strange, maybe, right? Because SLTI instruction, you can specify only 12-bit immediate, right? 12-bit immediate. But here it looks like you specified 32-bit immediate. So it may sound very strange, but you have to think about end result, ALU input, right? T1 and this value can be cooked up. This value ALU input can be cooked up inside the CPU, right? So check out this. Look at this. SLTI 8 Fs, then 12-bit immediate is FFF. So based on this FFF 12-bit immediate, sign detection logic can give you these 8 Fs. Does it make sense or confusing? So, the point is when you write assembly code, you write the code. So the intention, right? Intention of this code is what? You want to do, you want to compare T1 and this number. Okay, this number, right? This number, right? So that is your intention, right? And then the question is, that can be created. This number can be created by CPU based on RISC-V specification. Yes, it can be. Right? It can be created. So when it comes to the first instruction, your intention is you want to compare this one against this one. What is that one? 5 zeros, right? 5 zeros, 7 FF, right? Hex. So that is your intention, right? You want to compare T1 against that number. So the question is, CPU can cook up that constant? Yes. Based on RISC-V specification? Yes. If you go through that, hardware process, then you can create this number. A little confusing, but by the way, does it make sense? Okay, that is one thing, one important thing. And I gave you one example, right? When you can use those instructions. The first usage case, okay, you can use, so compiler will generate SLT instruction in this case. Okay, if you declare Boolean type local variables like this, then based on the condition, you set this Boolean data type, right? Then compiler will generate SLT instruction. We'll use SLT instruction to give you code. And if you are if you are not comfortable with this statement, probably you write this code, right? If A, B, then test 1 equal 1. Otherwise, test 1 equal 0. Probably you write this code instead of this one, right? This one may be more comfortable to you, right? This one and this one, same statement, right? If A is less than B, then test 1 is 1. Okay, okay, test 1, sorry. Test 1. So if you compile this code, let me compile this code. Some warning messages because I assigned test 1 here and assign test 1 here, right? So what is the purpose of this statement? You overwrite test 1 right here, right? Without using this test 1 in between these two, right? So warning message, right? It doesn't matter. Look at this. So in this case, look at this. In this case, compiler used SLT instruction. But in this case, compiler used branch instruction. And then a load immediate, depending on the condition, right? Load immediate to 0 or something. It's a little bit, complicated binary, okay? A little bit complicated. So if you give some option in makefile, compilation option like here, some optimization option like O2. So CC flag, compilation option. O2 means, there is optimization routine, optimization option. That means you are asking compiler, okay, do whatever you can do. Give me the best code, not, unoptimized. Give me the optimized one, okay, not, naive code. So if you do this, okay, check out this dump. Compare, right? Compare. What happened here? So we have C code, C code, C code, no corresponding assembly, no corresponding binary. Why is that? We put -O2, compilation option, right? Do whatever you can do. Give me best, code option, right? You know what? Why do you think so? Why compiler did not give anything for this statement? Check out this, check out this. So it seems like compiler completely removed the code, completely removed this statement. So why is that? Because it is not used, right? Test one is used, okay, set here, but not used. Test one is set here, but not used afterwards, right? Then why did you set test one here? Right? So that is why compiler, okay, I think this code is not useful. It is useless because you haven't used test one after assigning value here. After assigning value here, you never used. So compiler decided, okay, these are useless. So I will remove that code. Very smart, right? So how to prevent compiler from not removing, this statement? Simply you can do this. You can use, test one, right? You can use test one later on. So let's say B plus test one. How about that? Test one. How about that? B plus test one. So that is used. And A, you are returning A. So compiler cannot remove waiting test one. So that will be, this one will be useless because test one is overwritten here. So let me compile this code anyway. Okay, look at this. So compiler decided not to give any code for that statement because that test one is overwritten here. But look at this. What is this code? SGTG. So one code, right? SGTG. It looks like pseudocode. Okay, I mean, what is the code? SGTG. So let me send it to here. What is the code? Compile it. Here. Okay. What is the code? SGTG. B393 SGTG. Set. Okay, let me write. Okay, let me write. Because I don't want to interpret. I don't want to interpret this machine code to, based on that encoding, right? I don't want to separate OP code, function 3, function 7. I don't want to do that, right? We don't have time. So let me write. It sounds like it is using SLT. I don't know, F5, A5, A0 or SLT, I don't know which one is which, A5. I think this SLTU, A5, A0. So let me test. Is it A0? Similar, right? Similar, but not equal. Set greater than, oh, 0. Set greater than 0. Oh, okay. Thanks, Juyong. Set greater than 0. Very similar, right? B3, B3, B3. So, okay, set greater than 0. Thanks. So then it should be, what? Set greater than 0. So A0. Okay, let me use SLT U SLT A5 is destination as A0 then 0 SLT RD X0. Okay, sorry, X0 is it A0? I don't know. Let me test. Okay. Oh, okay. So same code, right? This one SLTG. Okay. Set what? Set 0. Okay. Set greater than 0. Okay. Set greater than 0. Okay. Same machine code, right? This one, these two. Okay. So the thing is, so compiler generated that instruction for what? For that a whole statement. If A is less than B and test is 1, otherwise test is 1. So compiler give you only one instruction for that if statement. Because we impose that optimization option, right? -02. Okay. Okay, test. Yeah, play with Eclipse. Okay, play with Eclipse. Thanks, Juyong. Okay, second usage case of SLT instruction. Okay, I'm not going to talk in detail about this. I'm going to leave it to you. But let's read that statement, overflow checking. Okay, this one, Chaeyeon, can you please, from here, overflow checking.
Overflow checking for unsigned addition requires only a single additional branch instruction after the addition. For signal addition, or for signed addition, if an operand sign is known, overflow checking requires only a single branch after the addition. This covers the common case of addition with an immediate operand. For general signed addition, 3 additional instructions after the addition are required, leveraging the observation that the sum should be less than one of the operands if and only if the other operand is negative.
Okay, SLT instruction can be used to check overflow. Okay, that issue is a little bit actually very complicated. Okay, if you are new to digital logic or computer, then overflow checking sounds pretty simple. But if you dig deep into the detail, then it is not that simple actually. Right? Overflow checking. So what is overflow? First, so we are talking about 32-bit CPU, right? 32-bit CPU. So ALU takes 32 to 32-bit and generate 32-bit output, right? By the way, for overflow checking stuff, you can check out again my book, chapter 1. Okay, this computer architecture or this digital logic design. 곳에 221. Scroll it down. This lecture 6 and 7, adder and subtractor. These two. Check out these two. Okay, for overflow checking stuff. But let me briefly. I'm not talking in detail, but let me talk very briefly about overflow checking. So computer is taking, right? 32-bit CPU is taking 32-bit, two 32-bit inputs and generate 32-bit output. And what is the range of numbers you can represent with 32-bit? Okay, 32-bit is too long, too big to write. So let's simplify this. Okay, to 3-bit computer, 3-bit. Okay, to make it simple, 3-bit. Taking two 3-bit, and generate 3-bit. And if you think these numbers as unsigned, right? Unsigned, then you can represent 0, 1, 2, 3, 4, 5, 6, up to 7, right? 0 to 7. You can represent numbers, right? 8 different numbers with 3-bit, right? 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 7 is 1, 1, 1. Right? So that is a range of numbers you can represent with 3-bit, right? That is number. So what if you want to do 2 plus 3 with that computer? You're supplying 2, you're supplying 3. Then you are expecting 5, right? 2 plus 3 is 5, right? Then, so a computer, right? This CPU can give you, 5. How come? Because what is the meaning of 2 plus 3? Starting from this position 2, you are moving 3 steps forward, right? 3 steps forward. 1, 2, 3. So 5. Computer can give you 5. But what if you want to do 2 plus 6? Then the output supposed to be expected output is 8. But look at this. The largest integer this computer can represent is 7. Right? So that means what? 2 plus 6 is what? Starting from 2, you are moving 6 steps forward, right? So 1, 2, 3, 4, 5. Then what? What do you have to do? There's nowhere to go, right? So you wrap around, computer wrap around like this. So computer will give you 0. So in this case, we got overflow situation, right? So the actual output is bigger than the largest integer this computer can represent. So we get that is overflow, bigger than, right? So if you hit the largest integer, then computer will go back. It is very natural, right? What is that? 8 is what? In binary, 1, 3 zeros. A 3-bit computer, okay, can give you 3-bit output, only that output, right? That is why you are going back, right? Wrap around, right? So that information is gone, right? That information is not provided through that output, right? But depending on computer, right? Like Intel computer, your desktop computer, and smartphone computer, there is a separate register inside the CPU. In x86 Intel, you have E flag registers. And a smartphone CPU, ARM, has some special register called CPSR. Essentially, these two are status. That is called, in general, called the status register. That is inside the CPU. Right? Inside Intel inside ARM CPU, you have those registers, and that information, right? That information is stored in this status register. In ARM case, you have 4-bit N, G, C, V bit. So that information that is carried out. If you think about this mass, right? This mass, 2 plus 6, 0, 1, 0, 2, 6, 1, 1, 0 plus, right? So 0, 0, 0, then no carry out, 1, 1, 0, carry out is generated, and 1, 1, 0, 1, so 0, and final carry out is generated, right? So carry out in this case 1. That carry out is stored, will be stored, okay? That is will be stored here. In smartphone CPU case. And Intel has very similar register. That information will be stored somewhere, okay? Carry information. And by software, you can you can look up, you can read this information, status information, then figure out, okay, I got overflow situation by reading this, carry out information. But unfortunately, RISC-V CPU does not have this status register. Okay, that means what? That means you have to check overflow condition yourself with that kind of code. Okay, and or that kind of code. For unsigned addition, you can check overflow condition with that code. So you want to add these two, T1 plus T2, then store into T0, addition, right? Unsigned addition, unsigned number addition. 2 plus 6 supposed to be 8. But if you got overflow condition, then output will be smaller than some number, right? Not supposed to be bigger. This actual output supposed to be bigger than this one or this one. But if you have overflow condition, then smaller than actual output is smaller, right? 0, smaller than this, right? So it is checking, right? T0 output less than, right? Less than BLT, less than T1, then that is overflow condition. So you have to check that with this code snippet, because RISC-V is not providing this kind of flag status register. Things would be a little bit complicating, right? So unsigned case, right? Unsigned case, it is very simple, right? Unsigned case, very simple. Okay, let me remove this. How about signed integer? Signed integer, same 3B computer, right? Then what is the range of numbers you can represent with 3-bit? So the smallest one, -4, -3, -2, -1, 0, 1, 2, 3. So 0 is obviously 3 zeros, right? 0, 0, 1, 0, 1, 0, 0, 1, 1. So what is -1 in 3-bit? 1, 1, 1. How come? Flip all the bits and add 1, right? Flip all the bits. 0, 0, 0, right? And add 1, then 0, 0, 1. That is +1. So that is -1. This one is -1. Right? So then what is this number? 0, 1, 1, 1, 0. Okay, -2. 1, 0, 1, -3. This one, 1, 0, 0, -4. Why -4? Flip all the bits and add 1, right? 0, 1, 1, and add 1. 1, 0, 0. That is minus plus 4. That is minus 4. Right? So the thing is, look at this. Let me write binary number here. 0, 1. Let me write all binary numbers here. 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Look at this. In this case, right? If you think of it as 1, 1, 1. If you think of it as unsigned, then that is plus 7. But if you think of it as same 1, 1, 1, right? Same 1, 1, 1. If you think of it as unsigned number, that is minus 1. Okay. So mapping looks like this, right? That is this one, 1, 1, 0, 1, 1, 0. Okay. 1, 0, 1, 1, 0, 1. Okay. 1, 0, 0, this one, 1, 0, 0. Okay, and 0, 0, 0 is this one. 0, 0, 0, and so on, right? 0, 1, 2, 3, same. 0, 1, 2, 3, 0, 1, 2, 3. So same principle applies to this unsigned number addition subtraction, right? For example, if you do one, what would be a good example? Okay, if you do 1 plus 1, like 1 plus 1, then you are expecting 2. So this computer can give you correct answer too, because it is not overflow. It is not overflow condition, right? So how to do this arithmetic addition operation? Starting from 1. Starting from 1, you go one step forward. One step, right? One step forward, right? So you are getting 2. No problem. No overflow, right? But what if you want to do this addition? 1 plus 3. You are expecting 4, but look at this. The largest integer is 3. So what happens? Starting from 1, you are moving 3 steps forward, right? 1, 2, then what? Nowhere to go, right? You wrap around. 1, 2, 3. So computer will give you that number, 1, 0, 0. 1, 0, 0 is what? Minus 4. Then you have overflow, right? So you have overflow condition. Okay, and that is overflow. And when it comes to subtraction, right? So you do something like this, minus 2. If you do, so in this case, if you do unsigned number case, if you do 3, 2 minus 4, okay, unsigned case, 2 minus 4, then what would happen? Starting from 2 minus 4, right? You are going 4 steps backwards, right? So 1, 1, 2, then what? Nowhere to go, right? You wrap around. 3 and 4. So computer will give you this number, 110. Then you have what? You have underflow condition. That is underflow. Here, overflow, underflow. But some people do not differentiate these two, on overflow, underflow. They simply say overflow. They don't differentiate these two. Okay, this is also overflow. This is also overflow. Okay, but officially this is underflow. This one is overflow. Same thing goes to here, right? If you do now, signed number arithmetic. If you do what 1, 1. Okay, so not minus 1, minus 2 plus minus 2 plus minus 3. Okay, so starting from 2, okay, you are moving 3 steps backwards, right? Adding but minus, right? So 1, 2, nowhere to go, right? You wrap around. So then you have on the flow condition, on the flow. Okay, the computer will give you this number. So the little little complex thing about this sign number arithmetic. So let me show you. This one, two is what? 110, right? 110. This one, okay. And then -3 is what? 101, 101. So add these two. So ALU will just simply do addition, right? If you write this code, right? So addition, right? 0, 1, 1, 0, 1, 1, this one, 0. Then you have carry out 1. So computer will give you this output. Then overflow, underflow actually, underflow generated. But you are not supposed to look at only this carry out, C3. C3, you have to look at C2, 2 carry out. Carry out from the last column and carry out from the second last column. And you have to do exclusive OR operation to check overflow condition for sign number. So in this case, right, carry out, this one is 0. Okay, carry out from second column. And the last column, this one is 1. So if you do 1 XOR operation, 0. What is XOR operation? Exclusive OR, right? So exclusive operation. Then this one is 1. So I'm talking about this flag, right? Talking about that flag. That will be set. So that is confusing point, right? Carry flag. This carry flag is used to check overflow of unsigned addition or subtraction. And V flag is used to check overflow of signed number. A little bit confusing point. Right? You have to differentiate these two. And when you design hardware after midterm exam, you have to cook up. You have to cook up that flag, because there are comparison instructions, right? Not only SLT, cell less than you compare, right? You compare, right? You compare these two. Also look at this BLT, branch less than T0, T1, then you branch to TL1. So you have to check T0 is less than T1. SLT, right? You think of these two as signed number. Okay, these two signed numbers, right? So sign number comparison by using those 4 flags. By using those 4 flags, you can tell which one is smaller. That is why I'm saying a little bit confused. So we don't have time to fully explain that comparison mechanism in computer. So I ask you to read the book or check out the PowerPoint. Okay, so it sounds like very simple to human, but it is not. Okay, in computer. So check out this. So look at this. So the time flies. Okay, so that is the E flags I mentioned here. I mentioned in Intel computer. Okay, you have overflow flag OF for signed number overflow checking, and you have carry flag that is used to check overflow of unsigned number, addition, subtraction, right? And yeah, explanation about this. Then we have smartphone CPU. Smartphone CPU has NGCV flag, right? This one, NGCV flag. Okay, so that is used to check the condition. Unsigned number, right? Unsigned number overflow. C. V. Signed number overflow. Signed number. Right? So the final table you have to look at. I think I have somewhere. No. So you take a look at this, right? Unsigned number higher, right? Unsigned, signed less than. Unsigned higher means unsigned higher, right? Unsigned higher. So for example, in C code, unsigned, right? Unsigned B, C. So you want to check this. B unsigned higher, right? C higher. This one. B is higher than C, unsigned numbers. If you want to check this condition, you have to look at C flag and G flag after doing subtraction. B minus C. Then based on that output, you can set so ALU will generate NGCV flag, NGCV flag after doing subtraction. Okay, do subtraction. Okay, do subtraction. Then by looking at these 4 flags, you can tell which one this condition is met or not. How? If C is set, okay, if C flag is set to 1, C flag is 1, and then 0 flag is 1, then this condition is met. You read this table like that. Okay, signed less than. You want to check out that condition. Okay, E and F, signed less than. Those are signed numbers. Signed numbers, integer, right? So think about that. Think about that. That is very basic and also elementary stuff in computer to understand computer, right? How does the computer do comparison? You have integer, right? How does the computer compare these two numbers and tell you, okay, which one is higher, which one is smaller? How can you tell? Very basic, right? Basic elementary stuff, but not that straightforward to understand, right? So read a book or check out this PowerPoint. And for coming back to RISC-V case, okay, RISC-V case. Again, RISC-V does not have this status register. So you have to write this kind of assembly code for signed number overflow checking. And this one is for unsigned number. This one, these two. Okay, addition, BLT, unsigned number, and this one for signed number overflow checking. Think about that. I think about this one is not that also intuitive, right? You have to think. Okay. Okay. Any question though? Time flies. Any question? We have 10 minutes. I want to talk about Endianness stuff because I want to jump to CPU design from next class. Okay, Endianness stuff is very simple. Show you. Endian stuff. This one. Let's read this first. Okay. All right. This one. Kyuwon, can you please? Okay, Juyong, Bang Juyong, can you please?
The terms Endian and Endianness refer to the convention of ordering bytes of a word in memory.
Then let's Haeju, can you please? Okay, Dongho, can you please?
Can you hear me?
Yes.
And should I don't know how to pronounce that, but
Big Endian,
Endians.
Endian.
Okay.
Okay.
Okay. Big Endian machines. IBM 360, 370, Motorola 68K, Spark, HP, PA. Little Endian machines. x86, DC, VAX, DC Alpha, RISC-V. The choice of Endians is completely arbitrary, but leads to hassles when sharing data between big Endian and little Endian computers. Why
Okay.
so messy? Blame early computer designers.
Okay. So Endian, thanks. Endian is very nasty issue in computer. The thing is, 50 years ago, 50. 50 years ago, when computer was built, very early days of computer, right? Very early days of computer manufacturer didn't talk to each other. For example, Intel, right? Intel built their own computer, and IBM they built their own computer, and they didn't talk to each other, right? And say, okay, Intel later on they found out, okay, I store this data, this way. Intel said, okay, I stored this data this way. IBM said, okay, I stored this way, opposite way. Oh, you did that? Oh, I did this the opposite way. Then what do you have to call? Okay, let's call this little Endian machine. Let's call this big Endian machine and let people know of this problem. So it is very nasty problem. So let me explain what is little Endian and big Endian first. Okay. Let me give you an example, right? So CPU, you have X2 RISC-V CPU. Okay, you have X2 register. Let's say you have 1, 2, 3, 4, 5, 6, 7, 8 stored. Okay, 32-bit data, hex number. Okay, so 4 byte. Okay, first byte, second byte, and so on. Right, that is stored in X2 register. And memory, right? You have location 0, 1 byte, right? Each one is byte. 0, 1, 2, 3, 4, 5, 6, 7, 8, same thing, right? A memory here, location 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay? So in Intel case, right? Let's assume that that is Intel CPU. Intel case, if you execute store order instruction, SW X2, let's say 8 X0. Let's assume it is Intel assembly, right? Even though it is RISC-V CPU, right? You are storing X2 location 4, starting from this location. Okay, you want to store this 4 byte here. So the issue is how to store, right? You store. So how to store this one? You store this LS byte, least significant byte, here or here? So what Intel did is, okay, I'm going to store this LS byte, least significant byte, okay, byte, least significant byte to low memory location, 4, 5, 6, 7, low memory location 4, right? 7, 8, then 5, 6, 3, 4, then 1, 2. That is what Intel did. Okay. How about IBM? That is Intel. IBM computer stored in opposite way. IBM computer starting from location 4. Okay, same. Okay, you want to store this data to here. Then what IBM did is IBM stored this one. Okay, this most significant byte. Okay, MS byte to low memory location. So 1, 2, 1, 2 here, but here 1, 2, 3, 4, 5, 6, 7, 8, like this. So here, okay, LS byte at low memory location, but here, MS byte to low memory location. So, because they didn't talk to each other, right? So later on, they found out, okay, I stored this data this way. And IBM said, okay, I stored this data in opposite way, right? Then what do you have to do? I don't want to change, the design. So what they did is, okay, we know this issue and we have to let people know of this issue and call this little endian machine and call this big endian machine. Very nasty, problem, right? Especially if you want to communicate between computer with different endian, right? Little endian machine, big endian machine. So you have to be careful. So easy way to remember is little endian machine, little end, right? This one is a little end. If you think of it as a number, big number, right? And that is influencing, contributing very small to this number, right? Little end, so little end. Little end goes to low address. Little endian. Big endian, big end. This one is big end. That is influencing a lot to that actual value, right? Big end. So big end goes to low address. That is probably easy way to remember, right? So very nasty issue. So let's go through one example. So by the way, IBM, Motorola, Spark, those computers are using big endian, and Intel x86 and RISC-V is using little endian. And then let's go through this example. This one, assume that S0 register. Assume that S0 register contains what? 2, 3, 4, 5, 6, 7, 8, 9. Okay. So after running this program on big endian machine, what value S0 will contain? Store S0 from location 0, right? Location 0. So big endian machine, 2, 3, big end goes to low address. 4, 5, 6, 7, 8, 9, right? And second code, load byte. You are reading 1 byte. From which location? Location 1. Okay. So you end up reading this one. This one will be stored in S0 register like this. What if you run the same program on little endian machine? Same program on little endian machine, same data, right? Here, look at this. Here, first instruction. Okay, you are storing S0, S02 here. So little endian machine, little end goes to low memory location 8, 9, 6, 7, 4, 5, 2, 3. Right? And second instruction is reading from location 1, this data, right? So you end up having 6, 7 in S0 register. So Endian is very nasty issue in computer, because early days of computer, they didn't talk to each other, right? Okay, that is about instruction discussion. Any question before wrapping up? 3 minutes. Yeah, please. Yeah, because you know what? We have 80 student, 80 student, 1 TA, right? 1 TA, should watch all 80, 80 80 videos, right? And each one is 3 minutes. Then how much time, right? 80 student, 3 minutes. Then 240 minutes. Okay, that is 3 hours. 3 hours. No break, right? 3 hours. That is why, right? One guy, 1 TA. Please help, right? Don't torture him, right?
Professor,
Yes.
do we have class next week
Yes.
on Monday?
Yes, we have a class on Monday, right?
Okay,
Because
thank you.
because we took off 1 week because of Thanksgiving holiday. We have to we have to have 15 week class. Otherwise, school, some issue with school. Right? Yeah, so we keep online class because we have more than 80 students. We have 80 students, right? To be offline class, we should have less than 50 students. So we will do yeah, we will stay online, right? We'll stay online. Okay, any other questions? All right, that's it. That's it for today, and see you on scope of midterm exam. Scope is it will cover the topics we will discuss on Monday, coming Monday. Right. So instruction and microarchitecture, first part of the CPU design microarchitecture. So everything actually we discussed before midterm exam. Okay, any other things? Okay, see you on Monday. Bye. Thanks.
교수님, 그
Mhm.
작년 시험 범위가 싱글 사이클까지였던 걸로 제가 확인을 했었는데 이번에도 동일할까요?
그러니까 이제 중간고사 전까지 얘기한 전체를 가 범위니까, 그러니까 월요일 수업 하는 것까지를 범위로 생각하면 되죠.
네, 감사합니다.
Alright. Stop.